So in a previous video, we determined the type of intermolecular forces between molecules by recognizing that all molecules have dispersion forces. That will be always a part of your answer. And then the second thing you're going to look at to see if the molecules are polar or nonpolar. If it's polar with a polar molecule, you would call it dipole-dipole. Polar with a nonpolar molecule, you would call it dipole-induced dipole. If it only had dispersion, that would be nonpolar with nonpolar. If you have a dipole-dipole, you should always check for hydrogen bonds. And that would be hydrogen bonded to fluorine, hydrogen bonded to oxygen, or hydrogen bonded to nitrogen. In this video, we are going to determine the strength of these intermolecular forces. If the molecules are the same size, then you can use this following key. Dispersion will be the weakest and hydrogen bonding will be the strongest. But a lot of times on the AP test, they give you two molecules that are different sizes. And so you need to be given some data such as melting point or boiling point, something that you can tell the strength because they are different sizes. Because it is possible that dispersion forces could be stronger than hydrogen bonding. If you have a very, very large molecule, the dispersion forces become stronger and stronger with more electrons because that electron cloud can shift around, and so your dispersion forces could be stronger than hydrogen bond. An example of London dispersion force strength would be that geckos can walk on the walls, and how they do this is through dispersion forces. So we might think that dispersion forces are weak, but they're not. If you have a whole bunch of them, they really add up to be very, very strong. Researchers at Stanford University even built a robot based on gecko's feet, and they're able to have this little robot gecko climb up some glass. As I said before, the strength of the intermolecular forces is measured in melting point. The opposite of that would be freezing point. So really they're the same point, but you're just going a different direction. If you're melting, you're going from a solid to a liquid. If you're freezing, you're going from a liquid to a solid. You could also look at boiling point or condensation point, which is the opposite of boiling point, to let you know. So the higher the temperature, generally, then the stronger the intermolecular forces. When we are melting something, the intermolecular forces are not completely broken. And that's because they're still a liquid. They're still held together. It's just that in a liquid, the intermolecular forces are constantly breaking and reforming. When we do boil something, going from a liquid to a gas, we are completely breaking those intermolecular forces. So you're going to see that something that has hydrogen bonding, it is going to have very, very high melting points and boiling points as compared to other molecules of the same size that only have dispersion force. Let's look at the strength of dispersion because there's lots of things to look at. Remember, dispersion or London dispersion or just London, you're looking at the shift of that electron cloud. So you have a temporary dipole that causes a chain reaction throughout your material that causes it all to stick together, or maybe you have some sort of polar molecule come and push it around. But the first thing that you can look at is what's called polarizability. And you don't have to define it. You can just say polarizability is the reason why. And what this means, this is the squishiness or the sloshiness of those electron clouds. If you have more electrons, then that means you have larger electron clouds, and that means you have an increased polarizability, and this means you have stronger attractions. So if the electron cloud is larger, then it can move around more and it can cause a more polar molecule. You can also look at the contact area or the shape of the molecule. This means you're comparing a molecule that is long and straight versus a molecule that is all balled up. The molecules that are all balled up, there's less surface area, and so because of that, then its stickiness is not as strong. However, if you have a very long molecule, it has lots of surface area. That means that you will have a stronger attraction between molecules and a larger induced dipole, and this means that it's going to have a higher boiling point because it has more dispersion force. And the third thing to look at is pi bonding. So remember, this is double and triple bond. So if you are looking at something that's single bonded, double bonded, or triple bonds, triple bond would have more pi bonding and therefore a stronger dipole or stronger London dispersion force. So here's some data tables that we can look at so that we can see this. These are all noble gases. And noble gases we know are all nonpolar. They don't form bonds, but we can measure their boiling points. And we see that the larger the cloud, that would be xenon, then the higher the boiling point. And that is because xenon is more polarizable than helium. Helium only has 2 electrons, while xenon has much, much, much more than that. And because of that, those electrons can get pushed around and stacked up more on one side of the atom than the other. And this is called polarizability. And so you're going to have stronger intermolecular forces in between those xenon molecules. In order to boil them, you have to come and completely break these. It is going to take 165 Kelvin in temperature in order to break that London dispersion force in comparison to helium. We have carbon bonded to 4 of the same element, and we are comparing hydrogen that just has 1 electron down here to iodine that has much more than that. And you can see that reflection in the melting point. Again, iodine is very, very large, and it can have its electrons shift much more than the hydrogen can, and that is reflected into stronger dispersion forces between the carbon tetraiodide molecules. So here's my attempt of drawing out these molecules, and you can see the sheer size of the carbon tetraiodide. There's just more electrons that can be influenced and pushed around, and because of that, you're going to get a very, very strong force between 2 carbon iodine molecules. Let's look at contact area, or the shape of the molecule. We see in this first case, there's lots of surface area. There's lots of opportunity for polarizability between the 2 molecules and those London dispersion forces, where on the second molecule, they're balled up, and so there's less contact area. So as a result, it is going to be easier to boil the second one than it would be the first one. This is showing the boiling point of different carbon chains, and we see that the C5 is long and straight and the C9 is long and straight, but the C9 is a much larger molecule. It's going to have more surface area. It's going to require more energy to completely break the dispersion forces in that C9 molecule. Let's look at pi bonding. Again, here's a data chart that we can look at this. We have alkanes, alkenes, alkynes, so single, double, and triple bonds. And we see that with the alkynes, it has a higher melting point and also a higher boiling point. And again, it's because of the pi bonding that it has. So here's another data table here in a series, and we can see at the beginning here, I'm just adding a carbon, and you can see how it increases that temperature. And I'm adding a carbon to the alcohols, carboxylic acid, and the ethers. And you can see that as the molecule gets longer, that increases the dispersion forces, and so that causes the boiling or the condensing point to be a higher temperature. You can also see evidence of hydrogen bonding, because you do have hydrogen bonding with alcohols, where all you have right here is dispersion. Along with the hydrogen bonding, you would also have dispersion and also dipole-dipole. It'd have all 3 in those alcohols. But you can see that much higher temperatures because of that. This one also, the carboxylic acid, also has the dispersion, the hydrogen bonding, and the dipole-dipole. And you can see it's even higher because it has 2 groups that can hydrogen bond, with this little oxygen hanging out here and this oxygen here. So just having double the amount of oxygen really increases that boiling point. And this last one, in a sample of ethers, you're not going to have hydrogen bonding, but you will have dipole forces. So I'll have dispersion and I will have dipole. I would not have hydrogen bonding because I don't have a hydrogen that's connected to a very electronegative atom. These oxygens are connected to carbons. So just dipole-dipole forces. Let's look at this second example down here. It says, why does benzene have a higher melting point than toluene? Well, toluene has this little group right here. So when these molecules are breaking apart to become a liquid, the benzene, they actually freeze in sheets that fit together just perfectly. And so as a result of that, it's harder to rip the benzene away. This little methyl group on the end, it causes the toluene to not stick to each other as well as the benzene does, just because of how it fits together in the surface area. And so as a result, it doesn't take as much energy to melt it. Let's look at this trend. So I want to start here with the purple. We see that as there are less electrons, that the boiling point decreases, or you can look at the other way. The more electrons, then the more, or then the higher the boiling point. These are all tetrahedral and they're all nonpolar. So we only have dispersion forces there. So that was the carbon family. Let's look at the next group, which they overlap here a little bit. Let's look at the nitrogen family right here. So you can see the larger molecules do have a higher boiling point, but then all of a sudden you see ammonia be higher. You would expect this. We're looking at the green line. You would expect it to be down here, but we don't see that. Instead, we see it's higher. And that is because NH4 has, or NH3 has hydrogen bonding. Let's look at the next family, the halogen family right here. And so you can see the HI, the HBr, they're polar, and so they're a little bit higher than the nonpolar purple line there at the bottom. But you do see HF. Again, you would predict that it would be lower down here, but it's not there. And that's because hydrogen fluoride also has hydrogen bonding. And let's look at the last family. So this is the oxygen family. And if you notice, water is up here, again, showing that hydrogen bonding trend. Again, if you looked at water, you would predict it would be here, but we find that it's not there. It is up higher. And again, it's because of hydrogen bonding. So all of these right here, these are polar. And so that's why they're a little bit higher than the nonpolar purple line at the bottom. But then you have hydrogen bonding of hydrogen with oxygen, hydrogen with fluorine, and hydrogen with nitrogen. Briefly, let's talk about ion dipole. It is not an intermolecular force, but it's just an electrostatic attraction. This occurs when ionic substances dissolve in water. The cations and the anions separate because the water molecules pull them apart. And we see the oxygen portion of the water molecule, it will surround the cation, and the anion will get surrounded by the hydrogen portion of the water molecule. But this is called an ion dipole. We've talked about this with lattice energy, but we see if you have just a +1 charge with a water molecule, it's a weaker attraction than if you had a +2 charge. You would have a stronger attraction with that water molecule.